Alright, today we're going to be talking about the Brouwer and Schauder fixed point theorems. I'm going to give a statement of the theorems and prove them. These theorems are essential for many existence results in nonlinear PDE. They don't necessarily guarantee uniqueness, but they do give existence in a lot of important cases. And we'll look at one of those cases after we prove the theorems. The Brouwer fixed point theorem states, let Xn be a finite n-dimensional normed vector space over the real or complex numbers. Let S be a compact and convex subset with non-empty interior. Then any continuous mapping A from S to itself has at least one fixed point. I will note that the assumption of non-empty interior is not necessary. S can be any compact and convex subset. The reason we're making this assumption is we want S to be homeomorphic to the n-dimensional unit disk, closed unit disk, and if S had empty interior, we could intersect S with a subspace of X to ensure that its interior was non-empty, in which case it would be homeomorphic to a lower dimensional closed unit ball. Alright, without loss of generality, assume that the field is the real numbers. In the complex numbers, we can just embed C in R2 and proceed. Since all norms on finite dimensional vector spaces are equivalent, we can take the norm to be the Euclidean norm. Note that this fact implies that all norms on finite dimensional vector spaces induce the same metric topology, and therefore our notions of things like continuity are going to be preserved. In particular, the Brouwer fixed point theorem is a topological theorem in its heart, and so the norm really doesn't matter here. Now, S is homeomorphic to the closed unit disk. You can build a homeomorphism via the Minkowski functional. What we're doing here is we're selecting a point in the interior of S to be our center of the closed unit disk, and then we're kind of constructing a ball surrounding the point and looking at all line segments passing through the point. Okay? And those line segments, because S is convex, those line segments are going to lie within S, and they're going to intersect S at a unique point on the boundary by the compactness of S. And so we're going to just scale every one of those line segments so that they are of length 1, and that's going to construct a homeomorphism continuous with continuous inverse between S and the closed unit disk. What this means, since fixed points are going to be unchanged with respect to homeomorphism, of course we're composing with the homeomorphism and its inverse. It suffices to prove the Brouwer fixed point theorem for any continuous map from the closed unit disk to itself. Okay. Now, in order to prove this case of the Brouwer fixed point theorem, we're first going to prove a weaker statement, which is that any differentiable map from the closed unit ball to itself has at least one fixed point. We're then going to use Weierstrass approximation to approximate the continuous mapping T by differentiable maps and show that the continuous map T must have a fixed point if all of the differentiable maps do. Let's prove proposition 2. Suppose that T has no fixed points. We can build a differentiable retraction onto the unit sphere by taking the unique point of the unit sphere which lies on the open ray beginning at T of x and passing through x. Since x and T of x are always going to be distinct by assumption that T has no fixed points, this ray is well defined and there will be a unique point passing through the boundary of which is the unit sphere. The map is differentiable. We can see this by varying T of x. Okay, by varying x, T of x will vary differentiably, and this open ray will vary differentiably. And since the boundary of the unit sphere is smooth, the intersection of the open ray with the boundary of the unit sphere is also going to vary differentiably. It's not difficult to show that R is a differentiable map. The problem is that such a retraction is impossible for topological reasons. But here we're going to show the impossibility of such a retraction using differentiable structure of manifolds. Okay, so denote the inclusion map I from Sn-1 into Dn, if we compose it with the retraction map, we're going to get the identity on the sphere. That's by definition of R of x. Remember, we're taking the unique point of the sphere which passes through x and starts at t of x. If x lies on the sphere, then that unique point is x itself. Therefore, the retraction restricted to the sphere is simply the identity. When we look at this map, when we look at the pullback on differential forms, we're going to induce a mapping from the differential forms on the n-1 sphere to itself, which is given by I star composed with R star. Okay. Now, recall Stokes' theorem. If we have a smooth n-1 form with compact support on an n manifold with boundary, okay, then the integral over m of the exterior derivative d omega is equal to the integral over partial m of omega. Now, in this statement of the theorem, there is an implied notation. When we're integrating over the boundary of m, okay, the form omega is defined on the manifold M, not on its boundary. The form on the boundary is given by the pullback of the inclusion map of omega. Okay, so this is kind of taken to be assumed in the statement of this theorem, but it's a very important fact, is that omega, we need to integrate forms on the manifold partial M. The form given by omega on partial M is simply the pullback of the inclusion map. Okay? Why is this important? Well, let's look at what we've just done with the retraction. Okay, because we can build this inclusion composed retraction map, when we pass to the integral over the sphere, we can write a volume form on the sphere as the pullback under the inclusion of a n-1 form r star omega on dn. Okay, so r star omega is an n-1 form defined on dn, given by the pullback of omega under the retraction map. Okay, since we can just insert I star composed with R star as its identity, we can write the integral over the sphere of its volume form as the integral over the boundary of a disk of the pullback of an n-1 form on that disk. Therefore, we can apply Stokes' theorem in this equality to pass to the integral over the interior of the disk of the exterior derivative of r star omega. And since the pullback commutes with the exterior derivative, we're going to get this expression r star d omega. Now, omega is a top form, it's a volume form. D omega is 0 because there are no n forms on the n-1 dimensional manifold Sn-1. Since d omega is identically 0, this integral will vanish, and we'll get a contradiction of the fact that omega is a volume form on the sphere. Okay? Alright, so here's a little explanation. These two paragraphs explain kind of the logic here. So this contradiction tells us that any differentiable map from the unit disk to itself must have a fixed point. Now let's show that actually any continuous map from the disk to itself must have a fixed point. We're going to use Weierstrass approximation. We start with a continuous mapping from the disk to itself without fixed points. By compactness of the disk, the infimum of the distance between x and its image under t is achieved at some point in the disk. Therefore, we can create a uniform lower bound between x and its image under t, that distance, and we're going to set this uniform lower bound to be 3 epsilon. Okay? So we're going to extend t to the entire space Rn. Okay, this is the t extension theorem, which says that since dn is closed, we can find this continuous extension. And then we're going to use Weierstrass approximation to find a smooth map t epsilon that's an epsilon approximation pointwise for every point in the disk. Okay? Now this epsilon approximation, since it might not map Rn into the disk, it's going to map Rn into the disk scaled by 1 plus epsilon. We can scale it back down so that its image lies in the unit disk by just scaling by 1 over 1 plus epsilon. then we can invoke what we've just shown, proposition 2, that this scaled map, the scaled smooth map, must have at least one fixed point. Okay, then we use the distance between this map and its fixed point and the triangle inequality to show that, in fact, the distance between the original continuous map T and x naught is going to be less than 2 epsilon. Okay, so let's just see how this is done here. I start with the distance from T of x naught minus x naught. Of course, x naught is a fixed point of this map T epsilon, so I'm invoking that here in this line. Next, I'm going to invoke the definition of this T twiddle of epsilon, which is the scaled definition. Invoke that scaling in the next equality. And then this inequality is a triangle inequality. Okay, so I'm taking the triangle inequality in this next line. And then finally, I just use the fact that this first term here is bounded above by epsilon because of our Weierstrass approximation, and the second term is bounded above by epsilon times 1 because the image of T is in the unit ball. Okay, and so this contradicts this uniform lower bound which we were given by compactness between x and T of x. So we conclude that no such uniform lower bound can exist, and therefore T, the continuous map T, must have a fixed point, given the fact that every differentiable map has a fixed point. Great. So this proves the Brouwer fixed point theorem. Let's move on to the Schauder fixed point theorem. First, we need some definitions. Let x and y be normed vector spaces over the real or complex numbers. A continuous mapping, T from x to y, is called compact if it maps bounded sets into relatively compact sets. Recall that a relatively compact set is a set whose closure is compact. Also note that a continuous mapping with compact domain is always a compact mapping. That's simply because we can use the compactness of the domain to show that any bounded set is going to get mapped into a relatively compact set. Okay? Of course, any bounded set in a compact domain is already relatively compact. Now, you need this finite epsilon net theorem. Let x be a Banach space and S a subset of x. The following two statements are equivalent. 1. The set S is relatively compact. 2. The set S has a finite epsilon net. That is, for every epsilon greater than 0, we can find a finite covering of S by balls of radius epsilon. And we're going to call the centers of this finite covering, the center points of these epsilon balls, are going to be our epsilon net. Okay? Now, to see the epsilon net theorem, it follows directly from the topological definition of compactness. We use the open cover of S given by balls centered at every point of S of radius epsilon, and we pass to its finite subcover, and that immediately gives us our epsilon net. For the backwards direction, you can consider a sequence in S, and now, for every epsilon greater than 0, we're going to have a finite covering of epsilon balls, and so by the pigeonhole principle, a sequence will have to remain in one of those balls, at least one of those balls, an infinite amount of time, and so passing to a subsequence, we can confine the sequence to an epsilon ball for any epsilon, which immediately gives us that the sequence is going to be Cauchy, and therefore that S is precompact. The last thing we'll need is the approximation theorem for compact mappings. So let x and y be Banach spaces over the real or complex numbers. Recall that a Banach space is a normed vector space which is complete with respect to that norm. Suppose S is a bounded subset of x. Let T be a map from S into y, and let it be a compact mapping. Then for every n, there exists a finite dimensional subspace Yn of y, and a continuous mapping Tn from S into Yn, such that the supremum of the distance between Tn of x and t of x is less than 1 over n, and Tn, the image of S under Tn, is contained in the convex hull of the image of S under T. This approximation theorem is going to come in handy when proving the Schauder fixed point theorem, because it allows us to approximate compact operators by operators with a finite dimensional image, and that will allow us to apply the Brouwer fixed point theorem to these approximate mappings, and then take the limit of their fixed points to conclude that T itself must have a fixed point. Let's prove this approximation theorem. Okay, by compactness of T and boundedness of S, we have that T of S is relatively compact in Y. Therefore, we can construct an epsilon net, T of x1 through T of xn. Now, I'm going to set epsilon to be less than 1 over n. I didn't include this in these notes, but epsilon needs to be less than 1 over n here. Okay. Alright, now I'm going to define the Schauder operator from S into Y, and this is given simply by a linear combination of these center points of our epsilon net, and the coefficients of the linear combination are these ak of x's, which are continuous functions from S into R, given by the following: max of 1 over n minus the distance from T of x and T of xk, and 0. Okay? So these ak of x's are continuous because they're compositions of continuous functions. You can see the norm is continuous, T is a continuous mapping, and then we're taking the max of a continuous function and 0, which remains continuous. Okay? Let me just... Okay. Now also the ak of x's are going to be strictly positive. Why are they strictly positive? Because by our assumption that epsilon is less than 1 over n here, this epsilon is going to be less than 1 over n, and so there will always be at least one point in our epsilon net such that this norm is less than 1 over n. And so when I take its maximum, I am going to get something greater than 0 for at least 1k, and so this summation is going to be strictly positive. Okay? And this is essential to show that Tn of x is well defined. Now the last thing that we'll note is that the image of Tn, okay, is going to be a subset of the convex hull generated by the n points of our epsilon net. This is essential because the convex hull of the n points which generate the epsilon net here is a finite dimensional subspace. Okay? It's contained in a finite dimensional subspace. So, of course, this is contained in the convex hull of the image of S under T. So these Tn of S's are going to actually be our approximations of T. Okay, and now we just use this definition of ak of x, which is cleverly defined such that this inequality holds. Okay, and therefore we can use the triangle inequality to bound the distance between T of x and Tn of x by 1 over n, essentially, just using some algebraic properties here in the triangle inequality. Okay, so it's just some clever linear combination of continuous functions against points in our epsilon net. This is going to be our approximation. Great. Let's move on to the Schauder fixed point theorem. Alright, let X be a Banach space over a field R or C, and let S be a closed, bounded, and convex subset. Then any compact mapping L from S to itself has a fixed point. To prove this, we're going to use the approximation theorem for compact mappings. Okay, so we construct an approximate map Ln whose distance from L is less than 1 over n for every x in S. Alright, now by the convexity and compactness of S, then when we intersect S with this finite dimensional subspace, we're going to get a compact convex set in the finite dimensional subspace, which we can then apply the Brouwer fixed point theorem to Ln, because its image it's working in an image which is compact and convex. Okay, so sorry, one second. Right. Yeah, so if we restrict Ln of S to S intersect Yn, we're going to satisfy the requirements for the Brouwer fixed point theorem, and we're going to get a fixed point of the approximate map Ln for every n. We take the sequence of fixed points of these approximation maps. The sequence is bounded because S is. By compactness of L, we get that the sequence L of y naught n is precompact, simply because it's the image of a bounded set under a compact map. Since it's precompact and S is closed, it's going to have a limit point that belongs to S. That limit point is Z. This limit point is ultimately going to be our fixed point, okay, of L. So, first we're going to check that the fixed points of the approximate mappings Tn actually approach this Z in the limit, okay? So here we're just using, the first equality is going to use the definition that Yn is a fixed point of Ln. And then we're going to apply the triangle inequality by adding and subtracting the mapping, the image of L, okay, of this fixed point Yn naught. Now this first term is going to 0 by definition of Z, right? Z is just the limit point of L of Yn naught. The second term is going to 0 by the approximation theorem. It's less than 1 over n for every n. So this term is going to 0 because ln's are an approximation of L. All right? Now we're going to look at the distance between L of Z and Z. Okay? If this distance goes to 0, we're going to get a fixed point. So again, we're going to use triangle inequality. I'm going to add and subtract L of Yn naught and Ln of Yn naught. And then I'm going to argue that these three terms all go to 0. This first term goes to 0 by the continuity of L. Okay, so since we've shown that Z converges to Y, or Yn naught converges to Z, then L of Z has to converge to L of Yn naught by continuity of L. Therefore, this term will go to 0. The second term here is going to 0 again by our approximation theorem. These ln's are 1 over n approximations of L. And this third term is going to 0 because, well, by definition, Yn naught is a fixed point, so this is just Yn naught, and we've already shown that Yn naught converges to Z. That was the first line. So all this goes to show that Z is indeed a fixed point of our mapping L, and this proves the Schauder fixed point theorem. One quick note. Going back to the discussion earlier, why can we apply the Brouwer fixed point theorem to Ln of S? Okay, so if we go back to the Brouwer fixed point theorem, okay, we need a mapping from a compact and convex set of a finite dimensional subset of a finite dimensional normed vector space to itself. Okay, so of course, in the proof of the Schauder fixed point theorem, this set is just S intersect Yn. It satisfies all the desired properties. Now, Ln is a map from S to this set. So it doesn't quite satisfy the conditions of the theorem, but if we restrict Ln to S intersect Yn, then we satisfy, right, if we restrict Ln to S intersect Yn, we satisfy the needed conditions for Brouwer fixed point theorem. And if you think about it intuitively, S is a larger set than S intersect N, so that being in our domain is not going to cause any problems in terms of finding fixed points, right? But yeah, technically speaking, I should have said that we restrict Ln to S intersect Yn to itself, and then we're going to get a fixed point. Okay, let's look at an application of the Schauder Fixed Point Theorem. This is something that was written elegantly in the Notes on Mean Field Games by this author Pierre C. I don't know how to pronounce the last name, so I won't try. You should check these notes out. They're really, really good, pretty advanced. I was struggling with them, but anyways, the idea is we're going to investigate a system of nonlinear PDE given by the following. What the system is modeling is it's modeling a player distribution, which is given by a probability distribution M of t. Now this player distribution is evolving in time, okay? It's a spatial probability distribution. It's evolving in time. And the point here is that given M of t, players are going to move according to their optimal value, according to some sort of value equation, which is given by 1 here, okay? So players are going to try and choose the optimal path to minimize a value function, and they're responding to the distribution, the total distribution of all of their players, M of t. So not only are they working in their own best interest, but they're also responding to how other players are playing the game. Now, specifically to the distribution of other players. And now, the second equation is how the distribution of players responds to how the players move according to their value functionals. So equation 2 is a continuity equation which governs the evolution of the distribution of players according to how they move with their value functions u. Okay? And so these two equations are very much coupled, and it's difficult to see how one might demonstrate, existence of a solution given the fact that you can't really analyze them separately as you would like. And the Schauder Fixed Point Theorem gives a bridge where one can analyze this first equation separately, show that for a given m of t there exists a unique viscosity solution to this first equation 1. And then once you have that unique viscosity solution, you plug it in to equation 2 and find a unique measure which solves this continuity equation. And so then you end up with a mapping from the initial distribution which you assumed that you already knew to the solution of this second equation. And then you basically prove this mapping is compact, and you find a fixed point. And once you find that fixed point, you're going to have a solution to the whole system. So extremely powerful because it allows you to kind of bridge the gap and use the extensive amount of analysis on equations 1 and 2 to your benefit. Okay, so the author here just assumes sufficient regularity conditions. I'll let you pause the video if you want to review the regularity conditions that are being assumed here. Okay. Great. So with these regularity conditions, we're looking for solutions, and then solutions which solve one u. The value function should be a viscosity solution with a first weak derivative that's bounded in supremum, and the second equation needs to be solved by m in a distributional sense. I mean, obviously it's a pair, but that's kind of the idea here. And now, to prove existence of the solution, this is the key kind of blip from the proof. The proof is like 10 pages long, but most of it is working with the separate equations themselves and analyzing these two equations separately. You can see here the author considers a convex subset of maps, which are maps which we take to be a time evolution of a probability measure. That's here. Okay, we assume we're given one of these maps M, and that satisfies the initial condition, and then we solve the first equation and we get the unique viscosity solution u to the first equation. With that unique viscosity solution in hand, we solve the continuity equation to get a new measure, mu. Okay, and the critical fact here is that the mapping from m to mu of these time evolving measures is continuous. Okay, not only is it continuous, we can actually prove that it's compact by essentially showing that the image of bounded sets is relatively compact, and namely that the image of bounded sets, because it satisfies these mu functions, are uniformly Lipschitz continuous. This is kind of like an equicontinuous condition, and because they are bounded and values in the compact set of probability measures, we can conclude pre-compactness or relatively compactness by something analogous to the Arzelli-Ascoli theorem, and once we have pre-compactness, we get that this mapping we've found is compact, so we can apply the Schauder fixed point theorem to find a fixed point, and that fixed point is going to solve the complete system that we started with. So really, really a beautiful and powerful example of how the Schauder fixed point theorem gets used to break down an extremely complicated coupled system into just analysis of the separate pieces, and then just showing that those pieces fit together in a way that gives someone a compact mapping. And yeah, I think this is just a wonderful example. This is where I kind of came into the Schauder fixed point theorem and started researching the theorem, and the proof of the theorem was because of these notes. So here are some references that I used to construct this lecture, and then of course the last couple slides on the applications, past the applications, those were physically taken from these notes on mean field games. So yeah, thanks for listening and have a nice day.